Hello and welcome. In this video, we're going to discuss about some of the advanced form of regression, Ridge, Lasso, and polynomial regression. Let's first begin by understanding the challenges with linear regression. First of all, linear regression has a major assumption that the variables are linearly associated. And if the variables do not represent a linear association, it would not be wise to fit a linear regression. For example, you can see in this image, the data that we have does not really follow a linear pattern. And in this case, if we try to force fit this red line, it will not be able to do justice to this data. Second is, linear regression is always very sensitive to the presence of outliers. So if you have extreme values that are very different from the rest of the data, they tend to affect the quality of linear regression. You can see it visually. This is a scenario where you probably do not have any extreme value and you have points already arranged in a line. So a line would be a good fit. Even if the points deviate a little bit, that will be acceptable because we work on minimization of a squared error in case of linear regression. But what if the scenario is like this? Some of the points are forming a line, and there is a specific point here which is very different from the rest of the points. Now, this point alone is trying to pull the line towards itself. So in the presence of outliers, the linear regression is not effective because the outliers tend to pull the regression line towards themselves, which changes the slope and intercept of a regression line in case of a two-dimensional data. And even in a higher dimensional data, when we operate on planes and hyperplanes, outliers do influence the outcomes of a regression. The third major opportunity with linear regression is that it is highly sensitive to the presence of multicollinearity. Multicollinearity is the concept when your independent variables are correlated. So we always want a scenario where independent variables are correlated with a dependent variable or the target that we are predicting. But we do not want a scenario where the independent variables are correlated with each other. And when that happens, the coefficients become unstable. And with our background, we understand that linear regression relies heavily on the coefficients. It values the variables based on their coefficients only. So if the coefficients become unstable, the whole idea or the credibility of linear regression goes for a toss. And it in turn affects the interpretability of the model. Now, how some of these opportunities could be overcome? Let's understand what's called regularization. Regularization is a term that's used to indicate that we are going to penalize our linear regression model coefficients. So now let's understand what are these regularization techniques that we are talking about, which are Ridge or L2 regularization and Lasso or L1 regularization. And then we'll also be discussing polynomial regression. First of all, Ridge regression applies the L2 regularization, also known as the L2 penalty or Ridge penalty. It tries to address the multicollinearity and overfitting issues in linear regression model. Now, what is an overfitting? Overfitting is a specific scenario where a model does great on the training data. When you showed X and Y labels both to the model, your model does extremely well. But in future, when you have to make predictions, you will not have the Y label available. You'll only have X's available or the independent variables available. When you make predictions, they may not be as accurate on the test data. This is the problem of overfitting. Your train performance was good, but your test performance is not so good. So Ridge regression tries to address both the multicollinearity and overfitting issues, and a couple of other issues with linear regression that we discussed earlier. How does it work? So we all know that linear regression works on the logic of ordinary least squares. It tries to minimize the sum of squared errors, the distance between an actual point and a point on the regression line. This is what an ordinary regression would try to minimize. But in case of Ridge, the loss function is a little more modified. It is not just the sum of squared errors. We are adding a penalty term like this. It has two parts. First is alpha. In some books, it will be represented as lambda. It's known as the tuning parameter. And these are the sum of squared coefficients. So a linear regression model would typically be using coefficients for every variable. These are the squared coefficients added up. Note, this does not include the intercept. It is only representing the coefficients associated with the variables. So what would happen? We are adding an additional penalty. The relationship between alpha and these coefficients is such that if alpha goes up, the coefficients would go down. And if alpha goes down, the coefficients would go up. Now, obviously, if alpha is 0, then we are not adding any shrinkage penalty. We are rather just considering the ordinary least squares method. So this is kind of a trade-off that we'll have to figure out what is the right value of alpha so that we are able to avoid overfitting. And why is this required? Why are we even talking about reducing the coefficients? As we know, linear regression gives importance to its features based on their coefficients. So if we are overvaluing a feature, how would we control it? By reducing the coefficients. So that's the whole logic. If you have features that you're overvaluing while training the data, then you have to control it so that your model stays generalizable. Another term for that is regularization. So it makes the model more generalizable so that even on the test data, your model is able to do justice. It's not just performing very well on the train set. So this is a visual depiction of how the coefficients behave in case of a simple regression versus ridge regression. So in case of an ordinary linear regression equation, you will not have any change to the coefficients based on the value of alpha because the loss function of an ordinary linear regression is not even utilizing alpha. It only is relying on reducing the squared error loss. Whereas in case of ridge regression, you would see as you change the value of alpha or the tuning parameter, the coefficients will tend to reduce, not necessarily touch zero, but they would almost approach zero. So this is the effect of increasing alpha. If alpha is zero, then you're dealing with an ordinary linear regression. And on the other hand, if alpha is infinite, then you're reducing the coefficients almost to zero. Now let's move on to the Lasso regression. And Lasso stands for least absolute shrinkage and selection operator. As you can see, it's using shrinkage, which means reducing the coefficients, and selection. So it also does a feature selection. It again addresses multicollinearity and overfitting issues by adding L1 penalty term. So if you remember, Ridge used an L2 penalty. Lasso uses L1 penalty. What does it look like? Let's just see this. So this is the same loss equation that you saw earlier. In case of linear regression, you would only concentrate on the ordinary least squares. But in case of a Lasso regression, you would also have a penalty term, which would be the tuning parameter times the absolute sum of coefficients. So coefficients could be positive, could be negative. We take their absolute values, sum them up, and multiply with this alpha. Once again, the relationship is similar. If alpha goes up, the coefficients will go down. If the alpha goes down, the coefficients will go up. We have to eventually find out the right value of alpha. So once again, comparing the coefficients, in case of an ordinary linear regression, you would find that the coefficients are not affected by alpha because this is not a term in the loss function. But in case of a Lasso regression, you would notice that the coefficients are not only reduced, but they can be reduced to zero. And this makes it capable of doing feature selection. So in a linear regression equation, if the coefficient of a variable is zero, it's as good as not having that variable in the model. You would notice that in case of ridge regression, these values were almost close to zero, but not exactly zero. Whereas in case of Lasso, these values can be exactly reduced to zero. So a quick comparison between Ridge and Lasso. Lasso has a feature selection property where some of the coefficients become exactly zero, and it can select a subset of the important features. Ridge tends to shrink all the coefficients towards zero, but rarely eliminates them entirely. So let's now understand how does the loss function look like. Let's say only two features, which have two coefficients, beta 1 and beta 2. And we are trying to keep them constrained so that the sum of these two coefficients is always less than or equal to some number s. Now, how does this geometrically look like? You can see this forms the shape of a diamond. As the value of s is increasing, the size of this diamond is increasing. So if you followed geometry, you would understand that if you remove the signs of these coefficients, these could be negative as well as positive. That's why you have four possible combinations of negative beta 1 and positive beta 2, positive beta 1 and negative beta 2, both positives and both negatives. If you try to look at this geometrically, this forms a region enclosed between these four lines. And as you can see, the size of this geometry increases as the value of s increases. Now, let's understand how does this look like for a ridge regression. Now, in case of ridge regression, if you take the x-axis as one coefficient and y-axis as the other coefficient, this looks more like x squared plus y squared is equal to a number, which is the equation of a circle. So as you increase the value of s, you can imagine the circle also grows bigger. So geometrically, Lasso looks like a diamond and ridge looks like a circle. Now, how does the loss function look like for an ordinary linear regression? Let's have a look at it. So typically in a multi-dimensional scenario, your loss function would take the shape of a bowl. It's kind of a paper which is a little rolled and it would be looking more like a bowl to you. But for easier interpretation, we can always take its projection on a two-dimensional plane. So you can imagine this is a shape formed by various concentric elliptical shapes. Now let us understand how does this ordinary least squared loss interact with the regularization or the penalty term. So this is an image taken from a very popular book called ISLR, and this is one of the best depictions to explain how Lasso could reduce the coefficients to 0, but Ridge was not able to. Look at the shape here. So this is a diamond shape that we discussed some time back, and this is how your ordinary least square loss looks like. We could get the coefficients by just the ordinary least squares. Plus, in case of Lasso and Ridge, we are considering these coefficients through the regularization terms. Now, we will settle for the value of coefficients where the ordinary least squares interacts with these regularization terms or the constrained region. You can imagine, owing to the kind of shape that the Lasso regression has, if the elliptical boundaries interact with this constrained region bound by Lasso, right at this point on the y-axis, which is essentially in this case the beta 2, you can see that it would have some value for beta 2, but the value of beta 1 here would be 0. So a 0 value for beta 1 is attainable if these elliptical boundaries intersect the constrained region right at this corner point. But you can imagine this would not be so readily feasible if the shape of the constrained region is circular. If the ellipse touches it here, it would always have some value for beta 2 and some value for beta 1. This would be something that you can write in terms of beta 1 comma beta 2. So I hope this gives you some visual intuition of why Lasso is able to reduce the coefficients to 0, but Ridge is not able to. You can imagine if these elliptical boundaries would have touched the axis here, then in that case, you would say there would be some value for beta 1, but the value for beta 2 would have become 0. But that again would not be exactly possible in case of this circular shape. So once again, summing up, Lasso is capable of reducing the coefficients to exactly 0, whereas Ridge would take them to almost 0, but won't make them exactly. Now let's move on to the polynomial regression. Now, polynomial regression allows us to model the non-linear relationships between the features. Like we discussed, linear regression has this one major assumption that the variables are all linearly associated. Polynomial regression is capable of handling those scenarios as well, where the association may not be strictly linear. And how does it do that? It does that by considering various degrees of the available variables. So it's no longer a scenario where x is just an ordinary term. Here, we could look at various exponents of x as well. And once again, we are putting it just in the form of an additive equation. So some people might argue why this is still called regression. Well, it is called regression because the relationship between the coefficients is still linear. You're still using the additive property of regression. You can say that this variable is x, and this x squared could be written as another variable x1. This x raised to the power n could be written as another variable called xn. So if you compare the equation like this, it is still looking like the equation that you would imagine in case of a multiple linear regression. Let's say we have two variables, x1 and x2. These are the predictors helping us predict a variable y. So what would a polynomial of degree 1 look like? Polynomial of degree 1 would have features such as 1 for the constant, x1 and x2. And what would happen if we have a polynomial of degree 2 with the same two features, x1 and x2? You can imagine it will use 1, x1, x2, and would also use x1 raised to the power 2 because this is a degree 2 polynomial. It would use x2 raised to the power 2, and it would also use x1 and x2, which is an interaction between the two. So you can imagine, in case of a multiple linear regression, you were only going to explain the y with the help of x1 and x2, plus you had a constant. But in case of a polynomial of degree 2, you're going to write your equation in terms of a constant plus coefficients of x1, x2, x1 squared, x2 squared, and x1, x2. So you have more coefficients here, more terms explaining an outcome. So in general, if we have a d degree polynomial with n variables, we will effectively create factorial of n plus d divided by factorial n factorial d features. Let's put some numbers to this equation. So we had a 2 degree polynomial with two variables, x1 and x2 in the previous case. So we'll put this as 2 and this as 2. It will become factorial of 2 plus 2, which is factorial of 4. And factorial of 4 is 24. And then we are dividing it by factorial of 2, which is 2 in itself, multiplied by factorial of 2, which is 2 into 2, 4. So 24 by 4 will give us 6 features. As you can see, 1, 2, 3, 4, 5, 6, 6 features. So this is a general formula so that you can estimate if you're taking a higher degree polynomial with certain number of features, how many features effectively you're going to be using. Now the question arises, when do we use polynomial regression? Of course, in cases when the data is nonlinear. Polynomial regression would offer a substantial advantage over a linear regression. You can see in this plot for this kind of data, which is presented by these blue dots or circles, a green line like this, which is a linear regression line, would not do justice. But this red curve fitting that you see here would probably do better. This red line represents the polynomial regression. It's more or less the same point here that in case of a nonlinear data, you may end up getting a lot of underfit through a linear regression model, but through a polynomial regression model, you'll probably get a better output. What could be the potential disadvantages of polynomial regression? Let's understand that. First of all, it can be prone to overfitting. Now, we always have to strike a balance. We don't want to be underfitting, and at the same time, we don't want to be overfitting as well, right? So it is quite possible that we may end up fitting such a complex polynomial model that it is no longer generalizable. And the last point is very important. It may not capture the true underlying relationship between variables and can produce poor fit if used inappropriately. See, we may understand the relationship between the weight of a child and the height of a child. But if we say that we are trying to explain the weight of the child with the height squared or raised to the power 3, you can imagine the interpretability would not be that high, and you may not be able to exactly understand the relationship between the variables to a great extent. So in terms of interpretation, still an ordinary linear regression would stay a winner. But in cases when the squared features or the interactions between the features actually have a meaning, a polynomial regression would be a good choice. All right, with this, we come to an end of our video on the advanced regression topics. Hope you had something new to learn from this. Thank you.